Hi everyone, today I'm working through question 16 part B from the Extension 2 trial exam held by Baulkham Hills in 2020. So I often find that the trial exams can sometimes be harder than the final HSC exams, particularly at selective schools like Baulkham Hills. So this being the very final part of the final question on this exam, it's no surprise that it's going to be a tough one. This part B has 3 subparts, so I'll work through each part in a separate video. So in this video we'll look at part 1. The setup to the question says that the real numbers A1, A2, A3 and so on are all positive, and for each positive n we have a capital AN and a capital GN defined as capital AN is equal to lowercase a1 plus a2 plus and so on up to an, all divided by n. And then we have the capital Gn as being equal to a1 times a2 and so on, all the way up to an to the power of 1 on n. So basically arithmetic mean and geometric mean, which is, I guess, what the capital A and capital G stand for. So part 1, which is worth 3 marks, asks us to show that for any given positive integer k, if, and then we're given this condition, lambda k to the power of k plus 1 minus k plus 1 times lambda k plus k is greater than or equal to 0, where lambda k is defined as lowercase a k plus 1 on uppercase g k, all to the power of 1 on k plus 1, if all of that is true, then we need to show that the inequality k plus 1 times capital A k plus 1 minus capital G k plus 1 is greater than or equal to k capital A k minus capital G k. Now that in itself just looks horrendous. A lot of stuff flying around. So you can see why it's worth 3 marks. But you can kind of tell just by the way things are being defined with this capital AN and capital G, and we're kind of being led to essentially what's probably going to be a proof of the AM-GM inequality. So this step 1 is clearly going to be some kind of scaffold so that we can prove this result that then lets us make use of it later to then do another proof. So yeah, let's take a look. So I've written out the key information here. I've kind of just put it in a different order to highlight what we're being asked to show, which is this inequality. And then everything else is just the information we can make use of to try and show this inequality. And as I mentioned, it's worth noting that really what we're dealing with is the definition of an arithmetic mean, or in other words, taking a whole bunch of numbers, adding them up and dividing by the total number of numbers that there were. And then we've also got a geometric mean, and that you obtain by multiplying all the numbers together and then taking the nth root, where n is the number of numbers. So there's something that you'll learn in 4 unit called the AM-GM inequality. It's quite a handy inequality to know, and it'll be no surprise that this question, when we work through all the parts, is leading us towards proving that inequality. But first of all, we need to prove this inequality. And I think the first step is to take what we're being given and just do a little rearranging to make it an inequality involving 0 on the right hand side, because often they're easier to deal with when you're trying to show something is greater than or equal to 0. And in this question in particular, because what we're given, what we're told we can rely on, involves a greater than or equal to 0 inequality, you can kind of see how getting what we want to show involving greater than or equal to 0 could be a handy first step. So what we'll do is we'll start by just bringing this k, ak minus gk over. So really what we're being asked to show is we want to show that k plus 1 times a k plus 1 minus g k plus 1, so that's this bit here, and then minus k a k minus g k, all of that we want to show is greater than or equal to 0. If we can show that, then we've shown this inequality. So I think let's just focus on this left-hand side, because in terms of the strategy for this question, I think if we can show that this left-hand side simplifies to this based on all the definitions, then we can say it's greater than or equal to 0, because we know this bit here we're told is greater than or equal to 0. So I think that's the strategy. Given the way everything's defined, we're going to encounter some pretty rough algebra, but I think as long as we're careful, I think we'll get there. I think the first thing to probably deal with, the easiest thing to deal with, are these A's, the capital A's, because here we've got a k plus 1 in front of an ak plus 1, and here we've got a k in front of an ak, and we know that each of these arithmetic means will be divided by, in this case, k plus 1 and k, so they're going to cancel, so things are going to simplify. So I think what we'll do, let's just expand these brackets and then try and simplify the arithmetic means. So here, I'll just do the k plus 1 into each item. So we'll have, well, let's just start by saying the left-hand side, we'll just focus on what's the left-hand side and come back to the inequality later, will be equal to k plus 1 times a of k plus 1 minus k plus 1 of g k plus 1. So that's expanding this bracket. Now let's do this one. So minus k ak, and then minus minus gets us plus k of g k. So hopefully that makes sense how I did that. Now let's bring the two arithmetic means just next to each other for convenience, and let's expand them using our definition. So this is going to be equal to k plus 1 times a1 plus a2 and so on, and I'll write the last two terms ak plus ak plus 1, and that's all over k plus 1, the number of terms, minus k of a1 plus a2 and so on up to ak, all divided by k, and then we've just got what's left over with our g's. So I'll just write it down here, minus k plus 1 g k plus 1 plus k of g k. And I don't think we need to worry about expanding these with their definition, at least not yet, because the thing we're trying to show in terms of these lambdas, lambda is defined with a gk in there. So actually it's probably smarter to leave the gk's as they are, at least for now. But in terms of simplifying what we've got, this k plus 1 will cancel with this k plus 1, this k will cancel with this k, and then what we're dealing with is a1 plus a2 and so on plus ak up to ak plus 1 minus a1 minus a2 and so on minus ak. So the a1 minus a1 will cancel, the a2 minus a2 will cancel, and everything in between will cancel all the way up to ak minus ak will cancel. So all of this actually disappears, and we're just left with this ak plus 1 all by itself. So our left-hand side really simplifies down to a k plus 1. Maybe I'll just keep it. So we'll go minus k plus 1 g k plus 1, and then plus k g to the k. And if we look at what we're now dealing with, we've got something minus k plus 1 times something plus k times something. And that's not too far off what we're heading to. Something minus k plus 1 times something plus k just by itself. So it kind of makes sense as a next step to try and get this k by itself. And one way we can do that is if we take this whole thing and multiply by gk on gk. So we're just multiplying by 1, but what that will serve to do is to cancel out these gk's and get the k by itself. So maybe what I'll do, I'll write this, I'll just bring this numerator gk over to the front. So we've got a gk times, and then I'll bring this denominator in under each of these terms. So we'll get an a k plus 1 on gk minus k plus 1 times gk plus 1 on gk, and then plus a k gk on gk. And the whole point of that was so that these two will cancel, and now we've got our k by itself. So we're one step closer because we're still dealing with something minus k plus 1 times something plus k now. And in terms of the next little simplification we can do, we can write this as gk times, and notice ak plus 1 on gk is the essence of what is lambda to the k. Except lambda to the k has a power of 1 on k plus 1. We don't have that 1 on k plus 1. So effectively, it's lambda to the k to the power of k plus 1, so that these two exponents would cancel, because you get k plus 1 on k plus 1 is 1. So really what we've got here is lambda to the k to the power of k plus 1. And that's good because that is the first term of what we're trying to show that this left-hand side is equal to, or at least can be written in the form of, so that we can make use of this inequality. Now, I'll leave the rest for now. So minus k plus 1 gk plus 1 on gk plus k. So now the next thing to really deal with is this. And you kind of know what we're going to be able to show it simplifies to. We're going to show it simplifies to lambda k, but we have to do the work to do it. But once we do, we'll have lambda to the k plus 1 minus k plus 1 lambda to the k plus k, and our inequality can be utilized. I might turn over at this point, and let's just focus on simplifying gk plus 1 on gk using our definitions. So let's turn over and say, let's note that gk plus 1 on gk, well, what is that equal to? Let's just write in the definition. So it's the geometric mean. So we're going to get on the numerator a1 times a2 and so on. And I might just write the last two terms. So let's write times ak times ak plus 1. And that's all to the power of 1 on k plus 1. And then in the numerator, in the denominator, we're going to get a1 times a2 and so on, just up to ak to the power of 1 on k. So that's just me inserting the definition of the geometric mean that we're given, just putting k plus 1 and k in the numerator and denominator. Now, what will be helpful is to isolate just the first k terms in this numerator so that we can then combine it with the denominator, which only has the first k terms, and then deal with this extra term itself. And that's pretty easy to do because we're multiplying. So we can say that this is just a1 times a2 and so on up to ak to the power of 1 on k plus 1 times ak plus 1 to the power of 1 on k plus 1. And then this is then divided by a1 times a2 and so on up to ak to the power of 1 on k. So hopefully that step makes sense. Now, the question is, how do we clean up these exponents? Because we've got the same thing being taken to the power of, maybe just in a new color. If we focus on this, the way you'd simplify it, the rules of exponents that you'd use is it's the top exponent minus the bottom exponent. So really we're looking at what is 1 on k plus 1 minus 1 on k. What is that? Well, that, if we just do a cross multiply, would be equal to k minus k plus 1 over the 2 multiplied, so k plus 1. So that's going to be k minus 1 on k plus 1. And these two cancel. So you just end up with a combined exponent of minus 1 on k plus 1. And I think you just got to be so careful there with your minuses and making sure you simplify. But from there, what we can say is that this is then equal to, and because it's a negative exponent, we can actually just put it in the denominator. rather than put it in the numerator with the negative, we can just put it in the denominator with a positive. So we'll keep this a k plus 1 to the power of 1 on k plus 1 up here in the numerator. That can stay. And then we get our a1 times a2 and so on up to ak to the power of 1 on k plus 1. So that's where we're at so far. Now what I'd like to do is, because I know we're trying to work towards lambda k, and I know that's ak plus 1 on gk, it'll be nice to be able to write, well, I've already got my ak plus 1 and it's got the right exponent. I'd like to be able to write a gk down here, and the good news is gk would be just a1 up to ak to the power of 1 on k. And we kind of have that because we can write this as ak plus 1 to the 1 on k plus 1 divided by a1 times a2 and so on times ak to the power of 1 on k, all to the power of 1 on k plus 1. So all I've done there is I've just broken out this 1 on k plus 1 into 1 on k times 1 on k plus 1, so one thing to the exponent of the other. Because now we can say, well, the top and bottom are both to the power of 1 on k plus 1, and really what we're dealing with is this ak plus 1 on the top and gk on the bottom, all to the power of 1 on k plus 1, and that is the very definition of lambda k. So that is equal to lambda k. So now that we've done this little side working, we can say therefore our left-hand side is equal to gk times, and we'll get our lambda k to the k plus 1, lambda k to the k plus 1, minus k plus 1, and then lambda k, minus k plus 1 lambda k, because we've just shown this is equal, so lambda k, and then plus k. Now, from here, this part we know is positive because we're told that's a condition. What we're really trying to show, we want to show that is true if this part is positive. So we know this bit here is greater than or equal to 0. And gk, by its very definition, we're told, we're dealing with positive numbers here, all multiplied, and then to the power of 1 on a positive number will also be positive. So we know gn in and of itself is going to be greater than or equal to 0. So if you take something greater than or equal to 0 and multiply it by something else greater than or equal to 0, you can say the whole thing must be greater than or equal to 0. So therefore we can say our left-hand side, which we started out with, was k plus 1 times ak plus 1 minus gk plus 1, ak plus 1 minus gk plus 1, minus k, ak minus gk. That's all greater than 0. And now we can bring this back over like how we started. So we can say, therefore, k plus 1, ak plus 1 minus gk plus 1 is greater than or equal to k, ak minus gk. And that's the very inequality we were being asked to show. So that's as required.
Sonic boom!
Alright, so that's that part 1 done. You can probably see why it's worth 3 marks and why it turns up on the very final part of the final question of the Baulkham Hills trial. I guess the key was not to be too daunted by all the symbols that are being thrown at you here. At the end of the day, the essence of getting this question was just being very careful with your algebra. None of this algebra is beyond a 4-unit student, I would argue. You gotta be super careful with your exponents, but the rules are, things you would have learned years ago and practiced many times. So it's really just, I would argue, this question is all about keeping your composure and just being very methodical and very careful. And that's easier said than done when you're up to the very last question of what's going to be a very tough exam. It's hard not to get fatigued, but I guess that's why we practice before we do these high stakes exams. We make sure we're kind of, you know, ready for it, you know, through practicing this kind of stuff over and over again, so that you get good at maintaining your stamina throughout the exam. So yeah, hopefully you're able to follow along with that and it all made sense. In the next video, I'll now take a look at part 2 of this question. All right, tick boom.